All right, so today is review day. The test on Wednesday, and we'll start early like we did with the last test, 7:20. I think the best thing to do today would be to first go through chapter 10, since that's the new material, and focus on the main things that you should know that either came out in the reading or came out in the lectures or comes out in the assignment, the practice problems, especially. And I do want to also look at those old exam problems as much as we have time for. And then we'll kind of backtrack and talk about other stuff. But since the chapter 10 is the new stuff, it'd be good to start with that, I think. Hang on here. So we got the spring 2018 old exam here and spring 2007 exam. I also shared with you. All right, so let's first quickly go through the reading and emphasize important points here. So first, as we talked about in class last Friday, there's the definition of a group homomorphism. A homomorphism phi from G to G bar is a mapping from G to G bar that preserves the group operation. It's operation preserving. Phi of A, B equals phi of A times phi of B. Nothing about being one-to-one, nothing about being onto. Yes, it doesn't have to be one-to-one, it doesn't have to be onto. Only operation preserving. The kernel of a homomorphism is the set of all elements that get mapped to the identity. Probably would have been better to denote that by an E bar. I think that's what I did in class. This E is the identity in the codomain, G bar in this notation up here. So it probably would have been better for the author to call this E bar. If your codomain has an identity element that you would identify as 0, either the number 0 or a vector 0, for example, then this would be the set of all things that map to the 0 vector, say the vector 0. And we'd be talking about the kernel of a linear transformation if you want to think of the vector spaces as being groups, which you can always do. You should be able to, for example, prove on the exam on Wednesday, as an example kind of thing you could do with this, prove that the kernel is a subgroup, in fact, a normal subgroup of G. G is a homomorphism from, say, G to G bar. That would be an example of something of an exam level kind of thing you should be able to do, is show the kernel of phi is a normal subgroup of G. That's definitely true and is definitely something you should be able to show. What would you use? What would you use to prove this? What comes to mind from chapter 9? Yeah, the normal subgroup test. What the normal subgroup test say to do? Well, first verify H is a subgroup. Or maybe you're given that it's a subgroup already. Okay, yeah, the subgroup test is saying, well, first, assuming H is a subgroup. When is it normal? It's normal when this is true. So technically, you'd want to show this is a subgroup in the first place. Maybe I wouldn't have you do the entire thing. Maybe I'd say, assuming this is a subgroup, use the normal subgroup test to show it's normal. Is it a subgroup? Well, is it closed under multiplication? It's pretty easy to show it's a subgroup. Yes, it is. If you assume A and B are in the kernel, then A times B is in the kernel because of this line of equations. And is it closed under inverses? Just like with isomorphisms, homomorphisms do have the property that phi of A inverse is the inverse of phi of A. And if you assume phi of A is E bar, this is E bar inverse, which is E bar. So it's pretty quick to show it's a subgroup. You'd also could show it's quickly non-empty because phi of E can be easily shown to be E bar. I haven't done that, but That's pretty easy to show, and you could use that fact. Then you'd want to show for an arbitrary x, say that aKer phi x inverse is a subset of the kernel. So give me something in here. This conjugate subgroup to the kernel is actually a subset of the kernel. Actually, it ends up equaling the kernel, but you only need to show this one inclusion to show that it's a normal subgroup. Do you remember in general when we write AH, A inverse, we call that a conjugate subgroup of H. In general, it doesn't equal H, but it will always be a subgroup of G. In the special case where it does equal H, that's when H is normal. But it's good enough just to show one inclusion. You don't have to show equality here, though they will be equal. If this is true, it turns out they will be equal. So you take an arbitrary element in here where it's x times something in the kernel times x inverse and show that product is in the kernel. It's fairly easy actually, using operation preserving properties, which are highlighted in chapter 10. Coming back to chapter 10. You got these two big theorems, similar theorems we had about properties of isomorphisms. Now we've got properties of homomorphisms. Homomorphisms still do map the identity to the identity. That was true of isomorphisms. It's also true of homomorphisms. Homomorphisms do preserve powers. That was true of isomorphisms. It's also true of homomorphisms. To prove this, you don't need to assume phi is 1-to-1 or onto. This is a little different than isomorphisms. Line 3 here. If the order of G is finite with isomorphisms, the order of phi of G equaled the order of G. But with homomorphisms that are not necessarily 1-to-1, they're not necessarily equal, but this one divides that one. You could get something smaller for the order. As an extreme example of this, by the way, if G and G bar are groups, there is always at least one homomorphism from G to G bar, and that is to map everything to the identity. That would be a homomorphism no matter what G and G bar are. By this, I mean map it for all little g. This is a homomorphism. No matter what G and G bar are. It is operation preserving. You can check that. For any groups G and G bar. What would the kernel of this particular homomorphism be? Should be easy. All of G maps everything in G to the identity. So that's kind of an extreme case of this. The order of phi of G for that homomorphism would always be 1 no matter what G is. And 1 does divide any other positive integer. So that would be an extreme example of that. Kernel is a subgroup, and ultimately it's a normal subgroup. Here's an important one. Well, actually, I mean, all of these are important. Phi of A equals phi of B if and only if the left coset of the kernel containing A equals the left coset of the kernel containing B. Phi of A, I mean, all these properties are things you should be able to prove on the exam. Phi of A equals phi of B if and only if this left coset equals this left coset. Think about this. It's an if and only if. We need two directions here. Suppose phi of A equals phi of B. How in the world would you show these cosets are equal? Properties of cosets is what you need. Remember that two left cosets, AH equals BH if and only if A inverse B is in H. which is also equivalent to B inverse A being in H. And again, the inverse does need to be on the thing on the left. If we were talking right cosets, then you put the inverse symbol on the right. So that's what we would need to show. We'd need to show A inverse B is in H, which is the kernel. Well, so go ahead and try it. Does this map to the identity? Is it in the kernel? Use properties of homomorphisms being operation preserving. We're assuming phi of A equals phi of B. So you could replace the phi of A in there by phi of B. Then you have phi of B multiplied by its own inverse. That's got to be E bar. So that's the idea of the left to right direction. The right to left direction essentially just reverses this logic. aKer phi equals bKer phi implies A inverse B is in the kernel. And I should have said here, this fact that these are equal means A inverse B is in the kernel. Yeah, just reverse the logic. Skip a couple steps. This ultimately means, well, I'm hardly skipping much here. Phi of A inverse times phi of B equals E bar, and therefore phi of B multiplying both sides on the left by phi of A equals phi of A. Okay, so these are just fundamental things you should be able to prove based on what we know about cosets and what we know about homomorphisms being operation preserving. Okay, these are pretty fundamental things. You'll see actually on the exam I noticed from 2018 that I talked about this on one problem in the context of differential equations. I think we should probably look at that problem. Not that you have to have diffie-q to understand it, but if I explain it, you should be able to understand it. If phi of g equals g prime, then what's this? Is that the inverse of phi applied to g prime? Well, wait a minute. Is phi being assumed to be 1-to-1 here? Those are kind of trick questions. Phi is not assumed to be 1-to-1 here. And phi inverse, in spite of the fact that it seems to be written here, is not assumed to exist. Don't remember if I mentioned this back first week of class or not. This is called the inverse image of the element g prime. It does not mean phi inverse exists when you write this. This is a certain, well, it's notation for a certain set. It's the set of everything in G that gets mapped to G prime. It does not mean phi inverse exists as a function. You can write this symbol, and people do, even when phi inverse doesn't exist, even when phi is not 1-to-1. It's just shorthand notation, again, for the set of all things in the domain that get mapped to, in this case, the element G prime. It's got two names. Sometimes it's called the inverse image of G prime. Sometimes it's called the preimage of G prime. But that is, this left coset is what the claim is. You should be able to prove this. Again, we'll talk about this stuff in the context of that exam problem very soon. Properties of subgroups under homomorphisms. Direct images are subgroups. Images of cyclic groups are cyclic. Images of abelian groups are abelian. And on an intuitive level, remember that we think of cyclic groups as being fairly simple. I mean, yes, they are the simplest kinds of groups. And abelian groups are, you might say, fairly simple. They're certainly more simple than non-abelian groups. Non-abelian groups include things like matrix groups under multiplication and stuff that get pretty complicated. They also include symmetric groups. And intuitively, you want to think of homomorphisms as sort of simplifying a group. When you got a homomorphism from G to G bar, well, at least if it's onto, but say not one-to-one, intuitively, G bar is kind of like a simpler version of G in a sense. Now that can be overinterpreted, but that's one way to look at it. And so since phi of H is a homomorphic image, it's simpler than H is in general. So yeah, if H is simple in being cyclic, then certainly its image should be. If H is fairly simple in being abelian, then certainly its image should be. That's not a precise way to think about these facts, but it's an intuitive way to think about it to maybe help you remember them. But these are pretty easy to prove as well. The direct image is more than a subgroup of G bar. It's also normal in, well, not necessarily all of G bar, but the image phi of G. That's a subtle thing here. Normality of a subgroup is always with respect to the bigger group. Let's say this is G and this is G bar. And I got a homomorphism from G to G bar. Let's say is not onto. So that's maybe the image phi of G, the set of all outputs of phi. And then you've got a normal subgroup H and G. It's going to get mapped to something smaller yet, phi of H. Phi of H will be normal in phi of G, but not necessarily normal in the bigger group. Not necessarily in G bar. I haven't mentioned that. Normalities of a subgroup is always with respect to one particular bigger group that it's a subgroup of. It's normal in this, but not necessarily in G bar. I mean, it might be normal in G bar, but not necessarily. The kernel, the size of the kernel is a measure of how badly phi is not one-to-one, say. If the size of the kernel is 2, then phi is a 2-to-1 mapping. If the size of the kernel is 3, if its order is 3, then phi is a 3-to-1 mapping. A 2-to-1 mapping meaning every output is mapped to from 2 inputs. A 3-to-1 mapping would be every output is mapped to from 3 inputs, etc. So the kernel kind of measures how far phi is from being 1-to-1, you might say. The size of the kernel. These two symbols, I mean, we can look at that one as well. These two symbols, once again, are inverse images. You're not saying phi inverse exists when you write these things. So if K bar is a subgroup of G bar, then this set called the inverse image of K bar under phi, writing with this notation, even though phi inverse may not exist, is the set of all things in G that get mapped to K bar, is a subgroup of G. And moreover, if K is normal, then this inverse image is also normal. If phi is onto and the kernel is the identity element, then in fact phi is an isomorphism. This is what this last one says. So the kernel being the identity is enough to say that phi is 1-to-1 is the point, which is pretty much equivalent to number 5. You should have, read about these things over the weekend. Listen to the lecture. related to these things. They should be somewhat familiar to you by now, but now before Wednesday, you want them to be, stronger in your memory. On Friday, we focused on the first isomorphism theorem. Mostly the mapping being well defined. We did not prove it was operation preserving. Instead of going over this proof, which you should understand, including the well-defined one, they're saying it's a consequence of property 5 of theorem 10.1, which is fine, though you got to know what that property is, and you need to understand how that works. It's actually this property here. Implies that it's well-defined, so you should make sure you think about that. You should be able to prove it's operation preserving as well. And really, it's just the definition of what this function is, as well as what it means to multiply cosets. That allows you to do that. And the fact that phi itself is assumed to be a homomorphism, so it's operation preserving. That's that equality right there. This other stuff, these other examples, I think are worth reading, but for sake of time, I'm not going to test you on it. I'm not going to test you on this NC theorem, for example. It's actually a pretty neat theorem in its applications, but I'm not going to test you on it because we just don't have the time. This is something you should know. Example 14. The factor group of Z by the cyclic subgroup generated by a positive integer n is isomorphic to Zn. I only realized over the weekend that last week I wrote this in a different way, which may have been confusing to you. Last week I wrote, I believe, something like this. And I never said what this was. This is common notation for the cyclic subgroup generated by 3. Because effectively you're taking everything in Z and multiplying it by 3. It's really like coset notation. So you can write that like that, or like this, or like the book does. If you've never known, IE is a Latin abbreviation for, well, I forgot what the Latin is, but it basically means in other words. Theorem 10.4 says normal subgroups are also kernels. If you've got a kernel, a normal subgroup of some group, it's automatically the kernel of some homomorphism, is what this is saying. And in particular, a homomorphism that maps an element in G to its left coset in the factor group is one example of a homomorphism that N would be a kernel of. Why? Well, remember, Gn equals N if and only if G is an element of N. That's true for any group, any subgroup, not necessarily normal subgroups. And also remember in the factor group that N is the identity element of the factor group because it equals En. So what elements get mapped to the identity here? Everything that's in N gets mapped to the identity. If G is in N, then Gn will equal N, which is the identity element of the factor group. And if G is not in N, then Gn will not equal N. It will not equal the identity element of the factor group. Essentially what this is saying in conjunction with the first isomorphism theorem is that studying homomorphisms and their images is equivalent to studying factor groups. They're really the same thing, the same idea thought about in different ways. Before we look at quick problems, just to remind you what's the purpose of all this. The purpose is classification, okay? Our purpose, at least. Classification is important for practical examples or practical real-life applications, you might say. It is good to know what possible isomorphisms classes there are, for example, of groups of order 60, because that can help you figure things out. Group theory is, for example, thought of as being the theory of symmetries. And one application I do remember reading about in the book is, like, for example, crystallography. So that's a physics/chemistry application. Essentially in crystallography, well, you are taking molecules and making crystals out of them, and you use lasers to help you decide the structure of the molecule in terms of, how are the atoms situated on the molecule. And that's done by looking at the symmetries of the molecule. Effectively, you're using group theory to understand the symmetries of the molecule. Like you probably read about or you should have read about the applications of, for example, the orbit stabilizer theorem to help you figure out possible symmetries of what was it, a tetrahedron or something? Or back in chapter 7. And that's application, or a soccer ball, application of group theory to symmetries. And that's, besides applications to the structure of the symmetries of soccer ball, you can imagine this has got applications to structure of molecules, for example. But that's not something I know much about. So we have to stick with the pure math. Our applications are to understanding classifying groups. And there are some classification theorems in these chapters that you should know. I guess in the end of chapter 9. You should know these for true, false, multiple choice questions, and maybe even a non-multiple choice or true, false question. Be able to use them if you need them, for example. If P is prime, there are only, up to isomorphism, 2 groups of order P squared. And they're both abelian. One is cyclic, Z sub P squared, and one is not. And these are not isomorphic to each other, right? Because P is not relatively prime to itself. So these are 2 distinct isomorphism classes of any group of order P squared where P is prime. And yeah, that does imply the corollary here, that a group of order P squared where P is prime must be abelian, because both of those groups are abelian. Don't forget that any group of order P, where P is prime, is, can you finish it for me? Any group of order P where P is prime, what can you say about it? For example, if G is a group of order 17, what can you say about it? Had it back in chapter 7. Got a guess even? The answer was fairly simple. That's a hint.
Is it cyclic?
Yeah, it's cyclic. Any group of prime order must be cyclic. There we go. Corollary of Lagrange's theorem. A group of prime order must be cyclic. Why? Because its only possible subgroups are trivial, the identity and itself. In other words, the elements have to have order 1 or the order of the entire group. And therefore, the ones that have order in the entire group must be generators. And therefore, the group is cyclic. All right, let's look at some of the old exam problems. And I guess while we look at these old exam problems, we'll also think back to previous chapters as well. Just do as much as we can in the time that we have. Let's look at the 2018 exam first, since that's more based on the lectures. Formula for an inner automorphism. That's just something to memorize. I will write it down now to remind you. Inner automorphism induced by a group element A is an automorphism that has that formula. So what does this test cover? For sure, it covers chapters 6 through 10. And this was in chapter 6. But you should certainly know things from previous chapters as well. Basic things like cyclic groups, facts about cyclic groups, and facts about permutations, for example, subgroup tests, 1 or 2 step subgroup tests, those kinds of things are things you should still know for this exam. So this is a chapter 6 idea. This is an isomorphism from a group to itself. By the way, this kind of isomorphism came up in another class before this point. What other class do we almost always refer to as something that came up before? Its initials are LA. Linear algebra. You do these kind of calculations in linear algebra when these A and X are matrices. You remember you were doing this kind of thing in linear algebra? Diagonalizing matrices, for example. This kind of inner automorphism, for example, could map a non-diagonal matrix to a diagonal matrix. Diagonalization with eigenvalues and eigenvectors it's related to inner automorphisms. That's just a side comment. Fully state Lagrange's theorem. Okay, the memorization thing. And again, you certainly can just spend the time memorizing things, but I've always tried to emphasize that if you understand stuff, you should be able to remember it without necessarily sitting down and memorizing. But if you need to sit down and memorizing, then you should. And I'm not looking for word for word. I'm looking for right meaning, same meaning. Stating either normal subgroup test or the definition of normality was in terms of left cosets being equal to right cosets. True false questions, I'll let you think about those. Yeah, here's the differential equations one. Yeah, maybe I wouldn't be able to ask you this without explaining it, but I could explain it right now. Let G be the group of all real valued infinitely differentiable functions on R. Note that the identity element is the zero function. By the way, this does come up in linear algebra as well. G is also a vector space under function addition. And the zero function, Z of t is always 0 for all real numbers t, is the zero element of this group. This mapping that maps y is a function here, a function of t. Maps y to y prime minus y, where y prime is the derivative of y. Turns out to be a homomorphism. It's operation preserving. Should be able to verify that. That's pretty quick. The group operations addition. The formula for phi here is map a function y to y prime minus y, where y is a function of time, t, say. So we got to map this to the derivative of the sum minus itself. I'm not bothering to write the t's in there, but I could. I could write of t's everywhere. And this prime is supposed to be differentiation with respect to t. You know from calculus that the derivative of a sum is the sum of the derivatives. So we can write this, and we can use the distributive property to distribute this minus sign through. And then we can use the commutative property of addition to rearrange here. And when I say addition, I also mean adding a negative. But hey, that's phi of 1 plus phi of y1 plus phi of y2. That verifies this formula is operation preserving. It is a group homomorphism. I just say in this problem it can be shown. Which of the following is the kernel? In other words, what gets mapped to the zero function is the question. Think about what phi is, where y prime is differentiation. Which of these sets of functions are going to get mapped to the zero function under this formula for phi? Take the derivative and subtract the function. When do you get zero? Is the derivative of the sine function minus itself equal to zero? No. Derivative of e to the t minus itself? Yeah, B is the answer. These are not as well. Their derivatives minus themselves do not equal zero. If I change the formula, then I could change the answer. If, for example, the formula were phi of y equals y double prime plus y, where y double prime is the second derivative, then the answer would be that one. Well, actually, that's not exactly right. That would be a subgroup of the kernel. I'd also have to include a cosine term in there. Sine and cosine are two functions whose second derivatives plus themselves always equal zero, right? Second derivative of sine is negative sine, and second derivative of cosine is negative cosine. So, I mean, what I'm saying here ultimately is group theory is related to differential equations, because these things, when this equals zero, for example, that's an example of a differential equation. Differential equations has plenty of applications to real life. Given a group G, a normal subgroup. Okay, so this is, I'm not going to go through this in detail. We did the other day, actually, last week. Your task is to identify two places where the normality of H is used in this line of equations here. Trying to show that the multiplication and factor group is well defined is the overarching purpose. Looks like an application of Lagrange's theorem there for 14. 15 is an application of that fact from chapter 7 about aKer. It is something I emphasized in the lectures. Haven't emphasized in here as much. In chapter 7, page 144, this fact here. Got two finite sets, subgroups H and K of a group. Define this set HK to be the set of all products like that. Then the order of HK is this divided by that. Note that HK is not necessarily, in general, a subgroup of G, but we can still talk about the number of elements in it. In the lectures, I do talk about internal direct products. I haven't mentioned internal direct products in here, so I think probably, even though it's in the lectures, since I haven't really emphasized it here, I should not put that on the exam. But just for sake of reference, the idea of the HK thing does come up in the internal direct products, which is in chapter 9, actually. Except, okay, imagine this definition in the context of two groups, two subgroups, H1 and H2. G is the internal direct product, and we would write G equals H1 cross H2, say, just pretend there's two of them. If G equals, if there's just two, H1, H2, that's the same as HK. In other words, every element in G is a product of something in the first group times something in the second. Then it would be a subgroup, it would be the entire group. And H1 intersect H2 would be just the identity. So I didn't emphasize internal direct products in here, we just haven't had time. It's in the lectures, but I think since I haven't emphasized it in here, it will not be on the exam. But just to tell you, it is related to that concept of this thing, HK. And you should know that formula from chapter 7. So you just do 8 times 12 divided by 2 here. Just know that fact, essentially. Oh, this is a fill in the blank about the proof of there being, of A4 having no subgroup of order 6, which actually is an important fact in group theory. As an example of the fact that the converse to Lagrange's theorem is false. So one thing Lagrange's theorem says is if H is a subgroup of a finite group G, then the order of H divides the order of G. It's also that fact about the number of left cosets. The converse would say if G is a finite group of say order n, and M divides n, then G has a subgroup of order M. That's a false statement. That's not true. And a counterexample is A4 has order 4 factorial divided by 2, which is 12, but no subgroup order 6 in spite of the fact that 6 divides 12. So this is actually a pretty important specialized fact in group theory, an example showing that the converse of Lagrange's theorem is false. And yeah, I think what I did here is the book actually did give this proof as well, though the book's proof back in chapter 7 is fairly short. I am wanting to fill in more details essentially here, and I'm wanting you to give reasons. So something I asked 3 years ago, I'm not ruling out asking you this exact same thing, so you should think about it. Let's see, this problem is about symmetric group S6, which is a chapter 5 thing. And yeah, I mean, still you should know earlier stuff. So you should know what S6 is. You shouldn't forget that. First, find the number of elements of order G that are 6 cycles, that are of order 6 that are 6 cycles. So here we are thinking about chapter 5 essentially. So this is more of an explicitly chapter 5 example. I think actually looking back on Moodle from 3 years ago, I did emphasize that exam 2 could definitely include things from chapter 5 as a pure chapter 5 question. I guess I'm not ruling that out for you either. So you should review the basics of chapter 5. And again, it's such an important topic. Symmetric groups, permutation groups, that it's worth re-emphasizing, worth restudying. And again, I think the best way to think about the theorems in that section are with examples. You don't have to know the proofs in chapter 5. So here we're finding elements of order 6 that are 6 cycles. Find the number of them. So it's essentially practice with the arguments that were in chapter 5 about how to count the number of elements of various orders. You got a 6 cycle, A, B, C, D, E, F, where if we're in S6, those 6 numbers are all the numbers 1, 2, 3, 4, 5, 6 in some order. How many 6 cycles would there be? S6 itself has 6 factorial elements, which is 720. How many of them are 6 cycles? Well, you've got 6 choices for A. You've got 5 choices for B. These do have to be distinct numbers, of course. You've got 4 choices for C. You've got 3 choices for D. You've got 2 choices for E. You've got 1 choice for F. But hey, that product can't be the answer, right? Because then you'd be saying everything in S6 is a 6 cycle. So what else do I have to do with this to figure out the number of possible 6 cycles? Divide by 6, and what's the reason for that? If I asked you for a reason, which I maybe wouldn't, but. Exactly. You can write this permutation in 6 different ways. That's one way. Here's another way. Here's another way, etc. Because of the ambiguity with the notation. So this is 5 factorial, which is 120. There are 126 cycles in S6. If it was S7, and you're still talking about 6 cycles, then this would be 7 times 6 times 5 times 4 times 3 times 2 divided by 6. Because there's still 6 ways to write it, 6 ways to write a 6 cycle. But there would be more of them because you'd start with 7 up top instead of 6 if we were in S7. Find the number of elements of G of order 6 that are products of 2 disjoint cycles. And remember, disjoint cycles commute. Well, you got 2 LCM facts in recent chapters. Chapter 5 is the one we're thinking about right now. There's also chapter 8 with external direct products. LCM of, an ordered pair, for example, is the least common multiple of the orders of the components. And in chapter 5, the LCM, or the order of an element written as a product of disjoint cycles is the LCM of the individual lengths of those cycles. So for products of 2 disjoint cycles, for it to have order 6, one of them would have to be a 3 cycle and one would have to be a 2 cycle. To think about the total number of these things, these are disjoints, so these are all distinct numbers. You'd have, say, 6 choices for A, 5 choices for B, 4 choices for C. But each such 3 cycle can be written in 3 different ways. Divide that by 3. And then for this one, you're left with 3 choices for D and 2 choices for E, and each one of these can be written in 2 different ways. Let me do some cancellation here. Ultimately, this is 6 times 5 times 4, which is 120. But is that the answer? Well, remember, disjoint cycles commute. This is the same as DE times ABC. So if we thought about it, let's see here. I'm feeling a little confused myself. The question is, do we need to divide by 2 or not?
I think we do. Because if you had S5, then you would say you have 120 elements.
Yeah, but we would start with 5 instead of 6. We have
Oh.
5 times 4 times 3 times 2 times 1. Divide that one still by 3 and this one by 2. I'll think about it. I think in the crunch here of class time, I'm feeling confused. Maybe I should not ask a question like this. Assuming you were able to get the answers to A and B, how would you do C? You'd have to add the answers to A and B to get the total number of elements of order 6. To find the total number of distinct cyclic subgroups of order 6, emphasis on the words distinct and cyclic, you'd have to divide your answer by 2 from the sum of the answers in A and B. Why? Because any cyclic group of order 6 has how many generators? What's order phi of 6? What are the generators of Z6, for example? 1 and 5, yeah. You divide by 2. Any cyclic group of order 6 has 2 generators. Here you're using facts from chapter 8. So those facts at the bottom of that one page that are not labeled as a theorem, but I said effectively you should label it as a theorem. These facts down here are things worth remembering for the exam. Know these for the exam. Again, page 161, chapter 8 at the bottom. So looking at this particular problem, number 18, 64 is 2 to the 6th. So that's this case. N is 6. Therefore, n minus 2 is 4. You'd have a z sub 2 to the 4th external direct product with z2. In other words, the external direct product of Z16 and Z2. Which, as I say in the hint here, is both m and n are powers of 2. And that, for example, would be a group of order 32, 60 times 2, which is the answer to B. Is it cyclic? Is Z16 external direct product with Z2 cyclic or not? Are 2 and 16 relatively prime? No, they're not. Therefore, it's not cyclic. We're using this corollary as well, ultimately, to say the thing I say in the first line, that this is going to be true for some m and n. So G has 16 elements. It's not cyclic. Use your previous work to determine how many elements of order 16 G has. That's where you'd want to think of the LCMs. The LCM of an ordered pair, or excuse me, the order of an ordered pair is the LCM of the orders of the components. You want to think about that for part D here. Maybe make a table like I do in the lectures. A table where you think about the order of A first, you also think about the order of B and the LCM, and then figure out the number of elements of each possible order based on that. And so, for example, when the LCM is 1 or 2 or 3, or 1 or 2, then there's only one element of that corresponds to that particular row in the table. But if the LCM, for example, is 4, then for that particular row, there would be 2 elements. Well, no, careful. I need to be more careful. You know, one way for the LCM to be 4 is if the order of A, if I'm talking Z16, if I'm talking the external direct product of Z16 and Z2, one way for the LCM to be 4 is when the first component has order 4 and the second one has order 1. There's only one choice for B, but there are 2 choices for A. Another way the LCM could be 4 is when this is true. A has order 4 and B has order 2. There's still only 2 elements here because there's still only one choice for B in Z2, the number 1. There's 2 choices for A, 1 choice for B, so total we have 2 choices. This doesn't apply to this particular example, but if you had some other example, like the external direct product with Z4 with itself, if the order of A was 4 and the order of B was 4, the LCM is still 4, but you have 4 elements here because it's two choices for A and two choices for B. That make sense? The LCM is still 4, but because there's two choices for A and two choices for B, if we're talking Z4, for example, elements of order 4 are the generators 1 and 3, both in the first component and the second component. So you've got two choices for A and two choices for B. 2 times 2 are 4 total elements in here of order 4. I just made that up as another example. It doesn't apply to this particular exam problem. And here's a factor group calculation like we did last Friday. Oh, here's something relevant to what we did just today. Suppose phi is a homomorphism from U15 to itself with kernel equal to this set. Suppose phi of 7 is 7. Find all the elements of U15 that map to 7. This is based on something that, at least in here, we only just did 40 minutes ago or something. Phi is mapping from U15 to itself. It's a homomorphism. The kernel of phi is the cyclic subgroup generated by 4, which happens to be a 2-element cyclic subgroup. Phi of 7 is 7. Find all the elements of U15 that map to 7. In other words, find the inverse image of 7. By one of the theorems in chapter 10, that inverse image, it's related to the kernel. Do you remember what it was? Talking about it 40, 45 minutes ago.
G times the kernel of phi, or little g.
Yep. Go ahead, Noah. Say it again.
G times the kernel of phi.
Yeah. 7 times the kernel of phi. That left coset. Since the kernel of phi consists of the elements 1 and 4, this would be 7, and 7 times 4 mod 15 would be 13. Right, 7 times 4 is 28. Mod by 15, you get 13. So 13 is the other element that gets mapped to 7. It must, because we're assuming phi is a homomorphism. So it's essentially just applying a knowledge fact there. We're about out of time. I do see here number 20, I had them prove the first isomorphism theorem, essentially all parts of it. And you should also quickly glance over the 2007 exam, or at least glance over it, but I would recommend working through things. In fact, look at number 4, we just did that one. Well, we didn't do it fully, but partially. You have to put the pieces together. Here we got 3 groups in the external direct product. More true false. Yeah. All right. That's all we have time for. Make sure you do fully study the one from 2007 as well. Have a good day.